In this video, we're going to investigate and introduce the idea of a Laplace transform, named after I believe, engineer and mathematician by the last name of Laplace. So let's give some motivation behind the Laplace transform. Oftentimes, we find that integration in our process of solving differential equations is time-consuming and or complicated. So we have to either perform multiple integrals, or the integrals are sometimes not easy to find in the state that they're in. Sometimes we want to use piecewise functions. For example, the Heaviside function, which we'll introduce soon, is incredibly simple to do comparatively using Laplace transforms and deal with than using standard procedures. And same goes for something known as the Dirac delta function, which is a very useful model for systems that have some sort of hard blow to the system that causes it to behave erratically for a second. And finally, if we can, let's avoid using integration as much as possible. That would be extremely convenient. So here's the strange definition of a Laplace transform. You'll have to bear with it because it is strange, and there are multiple ways to look at it. But a Laplace transform is a function, so it's a function, meaning that its output is not a single number or value. It is a function that's going to be output by this Laplace transform. So basically what we're going to do is we're going to take a function, and we're going to feed it inside as an input to the Laplace function. So imagine that here you have some function lying in your domain, and now you're going to take the Laplace of it, so you're basically going to feed that function as an input. So it's kind of like taking f of x, right? So x is the input value, and when you take f of x, that often involves doing something to it, for example, squaring it and adding 5. So the Laplace is itself an operator, much like f of x is an operator in a way. It's a complex operator. And then what happens is sometimes we call this resulting function capital F of s. So that's why we say the Laplace of f of t results in another function that we're calling cap f of s. And the reason we call it f of s is because now we're going to introduce, we're going to integrate out all the t's, and we're going to be left in terms of this variable s. Now s is just a constant, and we don't have to worry too terribly much about that, but it is important. And this is the Laplace transform is defined as taking the integral from 0 to infinity of our function multiplied by e to the negative st, where s is some constant. Okay, so right now that may not make sense, or why he developed this integral this way, but this is how it's defined. And pretty soon we'll see that these integration limits, 0 to infinity, are important, as well as the f of t times e to the negative st. That's important as well. So let's take a look at an example, the simplest case. Let's say f of t is just some constant. So what we're going to do is first of all, let's say that we want to find something even simpler than that. So rather than dealing with all constants k, let's say we want to find the Laplace transform of 1. So the Laplace transform of 1, that's the constant function, would be the integral by definition from 0 to infinity of the function 1 times e to the negative st dt. Okay, well, now we have to work through this Laplace transform. We have to work this integral, and so really we know that that's the integral of e to the negative st, which is going to be negative 1 over s e to the negative st, because remember s is just a constant, and that's going to be the integral from the limit of t goes from 0 to t goes to infinity. And we're finding the integral under the curve with respect to t. And now we have to make an argument about s. So what happens if I go ahead and evaluate this integral at t equals infinity? Well, I get negative 1 over s, e to the negative s times infinity. I know we're not supposed to do that, but we're supposed to say at the limit as t goes to infinity. And minus negative 1 over s, e to the negative s times 0. And that's easy easy enough to evaluate. Well, now we have to say, okay, well, you might say, oh, as t approaches infinity, this exponential function decays down towards 0. And that would be true as long as s is greater than 0. Because if s is less than 0, then we get something like negative 5, and that function actually looks like this. So s is really just what we call kind of a buffer constant. What it does is it acts as a fudge factor, so we can make an argument and say, well, as long as s is greater than 0, then this integral converges. And so this converges to e to the negative s infinity. That converges to 0. minus 1 over s e to the 0 is 1, and so that term goes away, or that term multiplies out to be 0, and we're left with negative 1 over s. And that's it. So now what we've just proven, which may not mean much to us at this point, but the Laplace transform of 1 is the resulting function 1 over s, which is strange, right? We took a Laplace of a constant, and we have what looks to be a rational function. Remember, s is itself a constant, so we've really translated a constant into another constant. Well, now what would this look like in general for k? We used, instead of k, we used 1. Well, let me do this. Let me just change the color here and go through and change all the 1s to k's. K, k, and now whenever we take our integral, we have a constant k up here, right? Because we can effectively factor out the constant, and so we get negative k over s, negative k over s, negative k over s, negative k over s. And so in that case, the Laplace transform of any constant would just be negative k over s. And so that should make sense, because when you're dealing with an integral, you can just factor out a constant. So oftentimes people will say, well, the Laplace transform of some constant is the same thing as factoring out the constant in the Laplace transform and taking the Laplace of 1. And the Laplace of 1 is 1 over s, so it would be the constant over s. So now what we're calling this is part of our toolbox of Laplace transforms. And we like this because notice that we've already done the integration one time around. We don't need to go back and do the integration again. In fact, we never need to do it if we're going to take the Laplace transform of a constant. So this is good news to us. What about an inverse Laplace transform? Well, an inverse Laplace transform works the same way. So if I take the Laplace transform of a function, then what I get is f of s. So again, we're calling that capital of f of s just to denote that when we take the Laplace of this function, we get another function that depends solely on s. So if we take the inverse of both sides, in other words, if I take the Laplace inverse of the Laplace, well, we already know what happens whenever you invert something. You take the Laplace of something and then you undo it, then you're going to be back at getting f of t. And so if you take the Laplace inverse of f of s, of the transformed function, then you're going to get back your original. So for example, if we take the inverse Laplace of 3 over s, well, hey, that looks an awful lot like the c over s format. In other words, I could factor out and make this 1 over s. And oh, okay, so what was the f of t function that gave me a Laplace transform of 1 over s? Well, that would be 3 times 1. And so the original function would have been 3. In other words, the Laplace of 3 would equal 3 over s. So the Laplace inverse of 3 over s must equal 3. And we need to know how to do this both ways, because we are going to be actually using both the Laplace transform and the inverse Laplace. And we need to know how to work backwards and forwards. And again, we could do the same thing with any sort of function. Well, let's derive a couple more here. So the Laplace transform of f of t equals e to the at. Okay, so again, we're going to set up the Laplace transform. Now, this Laplace transform is the same thing every time. The Laplace transform of well, let's instead of using a, use some other, let's just use a constant. Let's make this something that'll stand out to us, like let's do 7. Laplace transform of e to the 7t. So that was going to be, by definition, the integral from 0 to infinity, and look back at the definition if you need to, e to the 7t times e to the negative st, beautiful integral to try to take, since these can be combined. And now we have a product of exponential functions, same base, so we can sum the exponents, so 7t minus st dt. And what I will choose to do here is I'll go ahead and factor out, let's see, I'll factor out a negative t. And it's arbitrary. I'm just going to factor out a negative t. So I can make this negative t plus s, or s plus 1. S plus 7, excuse me. All right. And I think I have that. S minus 7, I'm sorry. And the reason I'm writing it this way is just because this is going to lead us to more conventional definition. You could factor out just a positive t and you'd end up with the same answer, but it's just by choice I choose to factor out a negative t. And now in order to integrate this, this is just a constant right here, right? So when I integrate an exponential function, this is going to be 1 over negative quantity s minus 7 e to the negative t times s minus 7. That's the integral of that. And I need to evaluate it on the bounds from 0 to infinity. And so what I'm going to do is evaluate it at infinity. So negative s minus 7 e to the negative infinity times s minus 7 minus 1 over negative s minus 7 e to the negative 0 times s minus 7. And what I notice that gives me is, okay, well, again, I need to make an argument here. I have to say that as long as s is bigger than 7, this will be a positive quantity here. And so you'll have a negative in the exponent. And so as a result, this guy will converge to 0. And this guy I can evaluate. So negative of a negative will just leave me with 1 over s minus s minus 7. Jumping the gun here. Right, so I have negative, negative. And then e to the negative 0 times s minus 7 is just 1. And so I get left with 1 over s minus 7. So the Laplace transform of e to the 7t is equal to 1 over s minus 7. And we're done. So now we never have to take the Laplace transform of e to the 7t again. We just know that it's going to be 1 over s minus 7. Now, of course, we're going to generalize this, right? Because 7 is just one potential constant that we might use. And what's the probability that we want to take the Laplace transform of exactly e to the 7t? Well, we can generalize this and we can say, hey, it looks like e to the at, if a were a constant, would just be 1 over s minus a. And we'd be totally right. In fact, if you just replaced 7 everywhere with a, and so on, the only difference would be that you'd have 1 over s minus a right here, and 1 over s minus a, and e to the at equals 1 over s minus a, and so there it is. And a is just a constant. Which also leads us to the fact that if I were to take the inverse Laplace transform of something like 1 over s minus 6, that would be e to the 6t. Or if I were to take the inverse Laplace transform of 1 over s plus 6, we'll notice that the sign here and the sign here is opposite, so that would just be e to the negative 6t. And there we have our next Laplace transform, and we're building our toolbox. So we never have to integrate. If we're trying to take the Laplace of e to the at, we've got it. We're done with that. And the Laplace of a sum or difference. Now, remember, all we're doing here is we're dealing with functions that both depend on t. And what that amounts to, by definition, is the integral from 0 to infinity of f of t plus or minus g of t dt, e to the at, e to the negative st dt. And so we know that the integral of a sum is the sum of the integrals, or the difference of the integrals. So this would be 0 to infinity of f of t e to the negative st dt by now distribute. And that would be plus or minus the integral from 0 to infinity of g of t e to the negative st dt, which is really just the Laplace of f of t by definition, plus or minus the Laplace of g of t. So this is one of the reasons why we like using this definition of Laplace transform, is because the Laplace of a sum or difference is the sum or difference of the Laplace transforms, which makes it extremely convenient to work with. And hopefully by now you can see somewhat of the value of choosing e to the negative st as that multiplier right there. Why did he do it? Well, the bounds of integration, if you've noticed in these last couple of examples, makes one of the terms often converge to 0, while the other term, that factor, converges to 1. And that's one of the reasons why we like the exponential function, because the exponential function in this definition of the integral helps us or allows us to pick virtually any f of t, and this integral will almost always converge. I want to say almost always because there you could probably find one, maybe if you tried hard enough, that would not converge, like something involving uh, functions involving factorials, like x factorial or something like that, where it could be uh, much more complicated. So in any case, but we don't run across those functions very often. And again, notice that here in our definition, backing up, again, this helped us converge. This term went to 0, and this term had a factor that went to 1, and that was extremely convenient because we ended up with something relatively simple. So that's why we like this definition, and this is where the Laplace transform is really the real deal. The Laplace transform of dy dt. Okay, well, we're going to see some magic happen here. So this, by definition, would be the integral from 0 to infinity of dy dt e to the negative st dt. And now it's not immediately obvious what to do, right? Because dy dt could potentially be any function. We've seen a lot of dy dt's. But here's the trick. If we use integration by parts, we can do some symbolic manipulation of this. So let u equal e to the negative st, and let dv equal dy dt dt. So that means the integral of this would be v equals y, and hopefully you can see that why I chose to let dv equal dy dt, and du would be negative s e to the negative st dt, because that's the derivative of it. And integration by parts says that this integral is equal to u times v, which is y times e to the negative st. Now, because this is has integration boundaries, this has to be evaluated from 0 to infinity, minus the integral of v du, which is y times dy dt. Oh, and sorry, this has to involve e to the negative st, and v du, excuse me, I take that back, so that shouldn't be there. V is y, du is negative s e to the negative st. And so now we could, we'll evaluate all our integrals at the same time. So this is y equals e to the negative st from 0 to infinity, minus the integral. Now I have an s in here, right? And s is a constant, so s can be factored out. And so I have a negative s, so that will make that a positive s, times the integral of y e to the negative st dt. And now I have right here, I can't do much with that because, again, I still don't know what y is. However, I can rewrite this term. I can say that, well, wait a minute, if f of t were y multiplied by e to the negative st, and this integrals from 0 to infinity, this is exactly just the Laplace transform of the function y. And now I could evaluate this guy from t equals 0 to infinity, negative s times infinity, minus y e to the negative s times 0. And also what I have to do is, because y itself is a function of time, I actually have to put in here y of 0 minus y of 0 e to the negative s times 0. And this guy, again, as long as s is greater than 0, converges to 0. And we're left with negative y e to the negative s times, y of 0. E to the negative s times 0 is 1, plus s times the Laplace of y. And at the end of the day, what we end up with is that the Laplace of the derivative is equal to s times the Laplace of y minus y of 0. And this is very, very critical right here. So, you know, the purpose of walking through this was just not to show you this cryptic formula, but to show you, and, you know, maybe you wouldn't think to do integration by parts, but the whole purpose of this is that we end up with this lovely thing here, which you notice that we took the Laplace of a derivative and we ended up having no derivatives left over. So in a way, you can think about this as this is how we're going to use this Laplace transform idea to solve differential equations. We're going to be able to take Laplace of derivatives, or functions involving derivatives, and reduce them down into their antiderivatives. And so the other beauty of this is that we get to plug in our initial condition right away. Y of 0 is precisely what we want to be as our initial condition. The handout, or on one of the handouts that we can have here is the set of different Laplace transforms that we've derived. So Laplace of e to the at equals 1 over s minus a. The Laplace of 1 equals 1 over s. The Laplace of t to the n, which we didn't derive, this one's a little bit harder to do, is n factorial over s to the n plus 1. And this is not n. It's not a very loud n. It just means that if n is an integer like 5, then it would be 5 times 4 times 3 times 2 times 1. Or if this were 10 factorial, it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's where the buck stops there. We've also found that the Laplace of a derivative is s times the Laplace of y minus y of 0. We showed that the Laplace of a sum is the sum of the Laplaces. And we showed that the Laplace of a constant times, well, it's really any function. The Laplace of a constant times any function. You can factor the constants out because the Laplace transform involves an integral, and we can factor or pass constants outside of the integral sign. Okay, so how is this going to come into play? Well, let's solve our very first our first differential here with Laplace transform. First differential equation with Laplace transforms. So here's the strategy. So what we want to do is we want to, 1, Laplace both sides. And we can do that, right? Because the Laplace of, if this side equals this side, then the Laplace of this side must equal the Laplace of that side. 2, isolate all L of y's. And 3, inverse Laplace. And we'll see in a second if this works. Now, the reason I picked this function is because we already know using separation of variables that the solution here should be ke to the 0.1 to the 0.1t. And we're just going to verify that this method will give us the same thing. All right, so here we go. The Laplace of both sides, I'm just going to write it out, equals the Laplace of 0.1y. Okay, so the Laplace of dy dt, I know that when we've just derived this, is s times the Laplace of y minus y of 0. Now, we don't do anything with the s. The s is a constant, so we'll worry about the constant later. And now we have the Laplace of 0.1y, which is the same thing as 0.1 times the Laplace of y. Now, the reason we are going to isolate the Laplace of y is that we can't do anything with these. It's impossible for us to take the Laplace of y, because that would mean that we know what y of t equals. Y is a function of time, and the Laplace is an integral with respect to time, so we don't know this. And so now what we're going to do is we're going to isolate the L of y's. Well, here I have an L of y term, and here I have an L of y term. And so what I'm going to do is I'm going to, well, first of all, plug in my constant. I know that y of 0 is equal to 0. Is equal to 10, pardon me. So the solution here would be 10 e to the negative to the 0.1t. So I have minus 10 equals 0.1 Laplace of y. And now I'll move my Laplace of y over to the other side, or similarly you could move this over here. I like to have my s Laplace of y term have a positive s on it. Minus 0.1 Laplace of y. And then move everything else over because we want to isolate it algebraically. So it looks like that. And now I'm still not done. I want to isolate it. So what I'm going to do is I'm going to factor it out, because each of these two terms has an L of y. And so I get s minus 0.1 equals 10. And I'm still not done isolating it. I want to divide out the s minus 0.1. S minus 0.1. And I get that the Laplace of y is equal to 10 over s minus 0.1. Now, you can hopefully see why we want to inverse this. We took the Laplace transform, we broke down, or we crumbled apart the derivative term and broke it into pieces that only involve its antiderivative term. And so now when I take the inverse of the Laplace of y, well, the inverse of a Laplace will be just the function, right? If I take the Laplace of y, I change the function, but then I invert it back, I get y again. And I need to take the inverse of 10 over s minus 0.1, which I can factor out the constant. It involves integrals and derivatives. We can do that. And so now what I have left is the Laplace inverse and the Laplace are opposites, so they are canceling operations, and I end up with 10. Well, now I have to think about what function, if I took the Laplace of it, would give me 1 over s minus 0.1. Well, that looks a lot like the Laplace transform of e to the at equals 1 over s minus a. Well, in this case, if a is replaced with 0.1, then a would be replaced with 0.1 here, and that means that the inverse Laplace of 1 over s minus 0.1 would be e to the 0.1t. And there we have it. That's the same answer we would have achieved by separation of variables. Now, in terms of whether you like it better, that's another story. But we didn't do any integrals. We were able to avoid integration by just doing some algebraic steps. So that is the process of working through Laplace transforms. And this is a simple case, but this works for more complicated ones. But before we pursue those, what happens if you have a inverse Laplace of 1 over, not, for example, anything that goes with our formula, our toolbox? We know that the Laplace inverse of 1 over s plus 1, we know is Laplace inverse of 1 over s plus 1 would be equal to e to the negative 1t. And we know that the Laplace inverse of 1 over s would be 1. But what is the Laplace inverse of the product? And we already know from calculus, we know that the derivative of f times g is not equal to the derivative of f times the derivative of g. And we also know that the integral of f times g dt is not equal to the integral of f dt times the integral of g dt. So we should know that well. We've learned our lesson many times. So unfortunately, there's nothing that can be applied here. We don't have a formula in our toolbox that is of the form 1 over s times s minus or plus something. Well, the trick here is partial fraction decomposition. And guess what? We're not going to do this by hand because it's painful, and it would take us much longer to go through this process. But partial fraction decomposition, what it does, PFD, works when there is a polynomial in the denominator. So a quadratic, a linear, a cubic, all these exponents are 1, so if you distributed through, you'd have a quadratic in the denominator. And this works out well whenever you do have a polynomial in the denominator. And what it does is it aims to separate out the two fractions, or the two denominators, via a process, and then it establishes what these coefficients are if that were broken up. And that's great. If we can break this up into two separate terms, we already know that the Laplace of, or the Laplace inverse for that matter, of a sum or difference would be the Laplace inverse of the sum of the Laplaces, or the sum of the inverse Laplaces. And so the way we're going to do that is we're going to jump over to Wolfram Alpha, and let's see if I can get one up here. So we'll go over to Wolfram Alpha, and I'll show you how to do this in here. Some graphing calculators are capable of doing this as well, but if you just type in a part for, I don't know why they say a part, but that's just a, you could probably even type in partial fraction. And you have to use x's. Focus on using, well, maybe you don't have to use x's. I like to use x's just because sometimes Wolfram gets confused if you use s's, and it tries to misinterpret it. But if you do partial fraction of 1 over quantity s times s plus 1, it seems to do the trick. So it says that the partial fraction decomposition is 1 over s minus 1 over s plus 1. Now don't think that you can just look at this and see that this would be the answer, because it's actually a little bit more complicated than it lets on. Finding these coefficients up here, they happen to be 1 in this case. One of them happens to be negative 1. It's not as easy to come by as you might think. So what we're going to do now is, in terms of writing out this, taking this inverse Laplace, is when we do get into the state where we do have a product of sort of mixed up functions in the denominator, we're going to be able to break that function up internally. So this is the same thing as taking the Laplace inverse of 1 over s minus 1 over s minus 1. Now that's going to be the same thing as the inverse Laplace of 1 over s minus the inverse Laplace of 1 over s minus 1, which is going to give us, well, the Laplace inverse of 1 over s is just 1. Laplace inverse of 1 over s minus 1 is e to the negative 1t, and bada bing, bada boom, we're done. That's the inverse Laplace transform of that. We'll do one final problem where this is going to come in quite handy and necessary. Let's suppose that now we start incorporating more terms. So this is something that you normally need to use integrating factors for. And we're going to proceed much in the same way, our strategy. Apply the Laplace, collect the L of y terms, and then invert Laplace the entire equation. So the Laplace of dy dt will equal the Laplace of 0.1y plus 2t. Okay, so Laplace of dy dt is s times the Laplace of y minus y of 0, which I know is 10, equals, and this is the other beauty of this, is that you don't have to go and solve for the arbitrary constant later on. You basically, it's part of your whole solution process all the way through. And then now this is going to be Laplace of 0.1y plus the Laplace of 2t. And of course, I can factor out constants, so that's 0.1 Laplace of y plus 2 Laplace of t. And here I'm just going to write s Laplace of y minus 10. And again, I'm going to work to collect all of my L of y terms, but I'm going to try to take as many Laplaces as I can. Now, this is the Laplace of t to the first power. Now, we didn't derive this one in this video, but we do have a formula for it. The Laplace transform of t to the n power is n factorial over s to the n plus 1. So, if we were taking the Laplace of t to the first power, that would be 1 factorial, which is just really 1 times 1, over s to the 1 plus 1, which is going to give me 1 over s squared. And there it is. I'm done. I get 1 over s squared. And now I can proceed to work this out. So I'm going to have, and notice that the Laplace of a constant was just 1 over s, and the Laplace of t to the first power ends up being 1 over s squared. So there's a little bit of a pattern there. And so I get s Laplace of y minus 10 equals 0.1 Laplace of y plus 2 over s squared. Again, we're going to move all of our L of y's over to one side because we're going to want to isolate it. So I'm going to leave, I like to have my s term positive, minus 0.1 L of y. And this is just my personal preference. I like to have this to be positive s because then when I end up dividing by it, when I factor out the L of y, like we did in the previous problem, then my s is positive, and if I end up with e to the at terms, I see it relatively quickly. I don't need to factor out negatives and all that stuff. And then I'm going to move the 10 over to the other side, so I get 2 over s squared plus 10. And now I can factor out an L of y. You notice this process is very much similar from one problem to the next. Not sure if you're liking this more or less than the other method, but it is a little bit easier in regards to integration. And now I'm going to divide both sides by s minus 1 equals 2 over s squared over s minus 0.1 plus 10 over s minus 0.1, right? Because we have two terms, we need to divide them separately. Now, this is over 1, so you might think this looks really complicated, but this can be simplified to 2 over s squared times s minus 0.1 plus 10 over s minus 0.1. And that's the Laplace of y. Now, at this stage, I'm ready to take the inverse. And so I know that if I take the inverse of this side, and I take the inverse of this side, the whole purpose of that is because the inverse of the Laplace is just the original function. And now I can take the inverse of each term separately and factor out the constant. So 2 times the Laplace inverse of 1 over s squared times s minus 0.1 plus 10 times the Laplace inverse of 1 over s minus 0.1. And hopefully you can see it already over here. This is going to be, this term I can already invert, and I know that that's going to be 10 times e to the negative 0.1t. However, this is going to require partial fraction decomposition because I have a polynomial in the denominator. So I'm going to take this and step over to Wolfram alpha and type in 1 over s squared times s minus 0.1, and here you're going to see that this is not at all intuitive how you would maybe come up with these coefficients. See, there it is. So we end up with that decomposing into 3 separate terms. Don't worry about it, that's just what the decomposition is, and this breaks it into manageable pieces. And so we get so 10, 100, 100, negative 10, negative 100, 100. Let's see, I might have to kind of come back a couple times here. Okay, so I've kind of copied and pasted things over here. It's a little bit sloppy looking, but this is 2 times the Laplace inverse of this, which is just the partial fraction decomposition of that right there. And I've already taken the liberty to just convert 10 Laplace inverse of 1 over s minus 0.1 to 10 e to the negative 0.1t. So I can already do a couple of these terms, so I know that y is going to equal. Now I'm going to leave the 2 out. Laplace inverse of, well, this is negative 10, so I can factor that out and make it negative 20 Laplace inverse of 1 over s squared. Minus, this is going to be 2 times 100, which is going to be minus 200 times the Laplace inverse of 1 over s, plus 200, because 2 times 100, the Laplace inverse of 1 over s minus 0.1, plus 10e to the negative 0.1t. Okay, well, this looks like a lot, but this is negative 20 times the Laplace inverse of 1 over s squared. I already know that the function that got me 1 over s squared was taking the Laplace of t. So this is going to be equal to negative 20 times t, right? Because, again, the Laplace of t to the first is equal to 1 over s squared. So the Laplace inverse of 1 over s squared must just be t to the first power. And then I've got the coefficient of negative 20. Now, negative 200, 1 over s. So 1 over s, the Laplace inverse of that is just 1. So I get negative 200 times 1. The Laplace inverse of 1 over s minus 0.1 we already know is e to the negative 0.1t. And then I have plus 10 more e to the negative 0.1t's. And I'm pretty much done here, other than I can just do some simplification. 200 plus 10 is 210 e to the negative 0.1t. And then I have minus 20t. So I've got those 3 terms taken care of, minus 200. And this is the solution function. This is what we would get by using integrating factors. And here we just had to use a bunch of algebra, which may or may not, you may or may not like that better, but it is a different technique. And in things like circuits, it makes a lot more sense to be doing Laplaces and Laplace inverses than it does to be doing things like integrating factors. So anyway, we'll go ahead and stop there. One thing I want to turn you on to as well is, what about the second derivative Laplace? The Laplace of the second derivative of the derivative of dy dt. Well, we know that the derivative of dy dt is s Laplace of y minus y of 0. And not terribly surprisingly, this is going to be s squared times the Laplace of y minus s times a y of 0 minus y prime of 0. And we'll introduce this a little bit more later. But again, the beauty behind the Laplace transform is that we can take even second order derivatives and we can reduce them down to 0th order derivatives, meaning we get it into just Laplace of y's. So we really like that. And that's it for Laplace transforms for now. More on this stuff to come a little bit later.